Hey guys, Miss Marusik here, and in this video, we're going to talk about constructing a Lewis dot structure for both atoms and ions. Now, Lewis dot structures are a helpful way of illustrating what an ionic bond versus a covalent bond looks like. For ionic bonds, we can show the electrons being lost and gained by our substances. We can show the ions that are present with their charge. For covalents, we can show the sharing of electrons. It's actually a really great way of illustrating the bonding structure. However, before we talk about how to do a Lewis dot structure with compounds, we need to first look how to do them with both atoms and ions individually. Now, to start us off here, I have a chart of some really helpful information that we're going to use as we construct these Lewis dot structures. The first thing I did is I broke my chart down into metals and nonmetals using our zigzag line of separation here. And you notice that on the left-hand side, we have our metals, except hydrogen, and on the right-hand side, we have our nonmetals. Now, the reason why it's kind of important to classify which type that we have is not only does that determine whether or not a bond is going to be ionic or covalent, depending on what's present in there, but also for ionic charges, remember our metals like to lose electrons and become cations, whereas our nonmetals like to gain electrons and become anions. So it's important to classify the difference between the two. The next thing I did is I went and identified for each group how many valence electrons the elements have in those groups. Valence electrons are the only electrons that we illustrate in a Lewis dot structure, so we need to know how many is going to be appropriate to show. So you notice group 1 has one valence electron. Remember, it's just that valence single s electron. For group 2, we have 2 valence electrons. I've skipped over the transition metals for a couple reasons. First off, we're very rarely asked to illustrate those, but also they would technically only have 2 valence electrons each, because by the time you're filling up the D sublevel, remember you filled up the valence S sublevel in a more valence shell. When we skip over here to group 13, we would have 3 valence electrons. Group 14 has 4, 15 has 5, 16 has 6, 17 has 7, and group 18 over here, I've put 8 because most of these have 8 valence electrons in the noble gas group, with the exception of helium. Remember, helium only has 2 electrons because of how small he is, and so those 2 electrons are its valence electrons. So we have to be kind of careful with the helium for a couple different reasons. All right, so next what I did is I indicated the common ionic charge that these groups typically have. Now, remember, when we are having to predict ionic charge, the idea is that most elements want to become isoelectronic with a noble gas, whatever the nearest noble gas would be. And so we'll either lose or gain electrons to become like that noble gas as far as electrons. So you notice here for group 1, I put a positive 1 charge because all of these elements would lose a valence electron to go back and look like the previous noble gas. Group 2 has a positive 2 charge. Group 13 has a positive 3 charge. So that should all sound pretty familiar because that's something we talked about in our previous unit. For our nonmetals, remember, they like to gain electrons, and so when they gain those electrons to look like the nearest noble gas that's in front of it, we end up with these negative charges of -4, -3, -2, and -1. Again, showing how many electrons have been gained there. Now, there's a couple areas where we have some kind of quirky things that happen. First off, let me talk about the transition metals. You'll notice for most of the transition metals, I did not put a charge. Why? Because they do various charges, and so a lot of times we have to be told exactly what charge they have in a particular situation. So it's not something that normally we have to predict. However, there are 3 of our transition metals that you want to be familiar with their common charge. And I always joke they make kind of a little staircase, and that's easy to remember them by. It's zinc, cadmium, and silver. Zinc and cadmium always do a positive 2 charge, whereas silver always does a positive 1 charge. So if you remember that group 13 is positive 3, here's where our little backward staircase comes in. We have our +3. We have 2 elements at +2 and then 1 element at +1. So if you kind of remember that little pattern there, that'll help you always get the charge of those particular ions. The other place that's kind of unusual are our metals that fall under the staircase. Now we don't have to worry about group 13. Those are always +3, so I don't have to stress about those having possible charges. But for group 14 and 15, you notice they could do more than one possible charge. For group 14, if they lose their valence p electrons, they would do a +2 charge. If they lose the p and the s that are valence, they would do a +4 charge. Same thing goes here for the ones that are group 15. +3 or +5, depending on if they lose just the valence p's or they lose the valence p and s electrons. I will warn you, there's only really a couple elements there that we see in that section that we have to worry about. In the +2 or +4, usually we have to worry about tin and also lead that are there. For the +3 and +5, it's antimony and bismuth are the two that we commonly see. Technically, these ones under here, we're not sure exactly what they would do. A lot of these are man-made elements that you won't see in compounds, and so we don't really have to worry about them. So we want to make sure that we are familiar with this chart, because this chart is really going to help us to be able to construct our Lewis dot structures. So you want to make sure that you get really familiar with the information that's on this chart. So with that said, let's go ahead and talk about constructing some Lewis dot structures here. Now, at the top of this, it does give us some guidelines for both atoms and ions. We kind of have to approach the two a little bit differently. There's some extra things that we need to process with ions, like their charge, in order to really figure out what's going on. So I'm going to start over here with some atoms, and then we'll talk about the ions next. So let's first start off with lithium. Now, the first thing you need to do is you need to figure out exactly who lithium is. So as a reminder, lithium is Li, and so I'm going to put down my symbol here, and there's going to be some things that I do around this symbol. So next what I would do is I would go find lithium on my periodic table, and I see lithium is in group 1. And if you remember that chart of information that we saw just a little bit ago, lithium being in group 1 means that it has 1 valence electron. And so what I want to do in my Lewis dot structure is show that valence electron. Now the way we're going to do that is by using dots, hence the name dot in the name. And so what I'm going to do is I'm going to pretend that there's an invisible box around lithium. Now in the first couple of these, I'm going to draw my box in just to help us visualize what that looks like. But as you get really good at these, you do not have to draw the box. And so what I'm going to do is I'm going to put 1 dot on one of the sides of the box to show that 1 valence electron. And it really doesn't matter which side you pick. So I'm going to put this dot on this side of the box, and I've now shown my 1 valence electron, and there is my Lewis dot structure. It's that easy. So now let's do another one. Boron. So we want to think about what element boron is. That would be B. And the next thing I would do is I would go and find it on my periodic table. I see boron is in group 13. And if you think back to our chart we filled out on the previous page, group 13 has 3 valence electrons. Now from here on out, I'm going to abbreviate valence electrons with just VE for valence electron, just to kind of help me remember what I'm counting there. And so again, I'm going to pretend I have my invisible box around boron, around the element, and I'm going to show my 3 dots, but I have to be really careful here. When I'm putting dots, it's almost like I'm following Hund's rule from our last unit, where we put 1 in each until we double up. Basically here we're following Hund's rule, where we're putting 1 on each side of this box until we double up. Now it doesn't matter which 3 sides you pick, but I'm going to put a dot on 3 sides of the box. So there's my boron Lewis dot structure. All right, next is oxygen. Oxygen, I know that the element symbol is O, and so I would go find oxygen on my periodic table, and I see oxygen is in group 16, and so that means I'm going to have 6 valence electrons here. So now, I'm not going to draw the box this time, I'm just going to envision the box, but I'm going to go and put one dot on each side of the box. And I see that once I've done that, there's 4 electrons, but remember, we need to show 6. So now I can start to double up and put these electrons in pairs. So it doesn't matter which 2 sides you pair up, but 2 of the sides should be paired while the other 2 are not. Now, what we're trying to show here is basically where are we going to have availability for bonding on versus where are we kind of filled up at? So like, for example, here on this oxygen is notorious for making only 2 bonds. And the reason why is because it's got a spot here and there that it could share. This is all full over here. Or for example, something like lithium, it's notorious for giving away that 1 valence electron because it's not paired up, and so that's not stable, and so it's likely to give that one up. We're showing some information that will help us eventually when we go and bond these up. All right, let's do one more atom together here on this top part. We're going to do bismuth, which is Bi. And I would come to my periodic table, and I see that bismuth is in group 15, so that means I'm going to have 5 valence electrons. And so I'm going to show my 5 dots. 1, 2, 3, 4. Now for the 5th one, it doesn't matter where you double it up. You could double it up on top, you could double up on the side, on the bottom, on this other side here. You just want to pick a side and double up. So 3 of the sides should have single dots, and 1 of the sides should have a double dot or a pair of dots. All right, now let's go ahead and talk about ions for a little bit. So we drew all these atoms here, but now we are going to want to transform these into an ion. And there's some special things we do to show it has become an ion. First off, we're going to address how many electrons are lost or gained as we draw our number of dots. But if you notice up here, it also says that we're going to put brackets and a charge on our Lewis dot structure. And that's to show that it's become different than the atom that we started with. So for a lithium ion, I want to think about, well, hey, what group is lithium in? That was in group 1. And I remember that the common charge of something in group 1 tends to be a positive 1 charge. Well, let's think about why. What does a positive 1 charge mean that's happened? Well, that means that I have lost 1 electron. That valence electron has been removed, and now the previous energy level is full. It's gone back and looked like helium as far as having its valence electrons now. So what we're going to do is we're going to think about, well, if I had 1 electron to begin with, and I'm losing that 1 electron, what does that leave me with? Well, that leaves me with nothing. So what I'm going to do is I'm going to draw my lithium here. But I'm going to actually show no dots. Why? Because I want to show what the original valence shell looks like now. Originally, it had 1 in that valence, but it lost it, so now it's empty, and that would indicate that the previous energy level is now the full one. However, I can't just leave it like this because obviously I haven't shown any dots, and so I need to show that this is kind of a special situation, something that's lost that electron. So to do that, I'm going to put brackets around it, and then I'm going to show our positive 1 charge. Now, with positive 1, you could just put a positive sign. You don't have to write the 1. Some textbooks will also show 1 positive. They'll put the number first and the sign second. But at bare minimum here, you would need to put your sign. All right, next, let's talk about boron. Boron is in group 13, and we said on our previous page that group 13 is notorious for making a positive 3 charge. Well, what does that mean that's happened? Well, that means that I have lost 3 electrons. So if I had 3 electrons to begin with, and I lose those 3, again, that means I end up with no valence electrons. So I'm going to put my boron in the middle here. I'm going to draw no dots to show that it lost all of those. I'm going to put brackets around this. and then I'm going to show my +3 charge. So notice that a lot of times metals, losing those electrons will often end up with no dots, especially if I'm predicting the charge of it. Now, if I'm being told the charge, that can create a different situation. So we'll see one of those here in a little bit. But if I'm predicting the charge of a metal, or if something I know that's going to become a cation like boron, then I'm going to end up with no dots. All right, so now let's talk about oxygen. Oxygen is in group 16. Well, I also see it's a nonmetal, and I know nonmetals typically gain with the exception of boron. Boron's kind of a weird one there because of how many valence electrons it has. And so therefore, this oxygen is going to gain 2 electrons to look like neon. I know that group 16 has a -2 charge. And again, the reason why it has a -2 charge is because it gained 2 electrons. Okay, well, if I had 6 valence electrons and I'm gaining 2 more, that means that now I'm going to have 8 valence electrons in that valence energy level. So I'm going to come over here and put my oxygen symbol down. This time I'm going to put all 8 dots. So 1 on each side, and then I'm going to double up. Although when they're all full like this, it doesn't really matter how you draw them. And then I'm going to put brackets and my charge of -2. So you notice on the nonmetals, because they're gaining electrons, they will often have all of these electrons filled up as an ion. So atoms, you're probably not going to be all the way full. But ions, there's a pretty good chance that if you are predicting the charge, that you're either going to be totally empty or totally filled up, one of the two. Now, there are situations where that's not the case. For example, let's talk about bismuth ion here. Remember, bismuth is in that unusual section that can be either +3 or +5. It's under the zigzag line of the group 15. It's a group 15 metal. And so what they've done here is they've told us exactly what charge to use. They've said, hey, we're going to use a +3 here versus the +5. We're telling you exactly what to use. Well, what does that +3 charge mean? Well, that means I have lost 3 electrons. Well, how many did I have to begin with? Well, if I look back over here, bismuth originally had 5. And so I'm like, okay, well, if it had 5 valence electrons and I'm losing 3 of those, that means I'm still going to have 2 valence electrons here. So when I draw my bismuth, I'm still going to have 2 dots. So again, if you're being told what charge to use, there is a chance that you may still have some dots remaining. And then of course I'm going to put my charge here. All right, so here's what I want y'all to try out. There's a whole bunch of other examples down at the bottom of this. With the exception of helium, we'll talk about helium here in just a moment. I want you to go ahead and pause the video and see if you can try out these other 7 atoms and ions. So go ahead, pause the video, and see if you can try those out. All right, did you pause it? Did you try them out? I sure hope you did. So let me go ahead and put my answers up here, and so you can see how you would compare. So for antimony, we had another one where we had 5 valence electrons. So again, one of your sides should be paired up. The other 3 are going to be single. Doesn't matter which side you made paired and which side you made the singles. However, here again, they've told us what charge to use. Antimony could be a +3 or +5. They've told us here +5. But you notice here that would lose all of the valence electrons that I had. So I end up with no dots and a +5 charge. For phosphorus, again, we have 5 valence electrons. It was in group 15. But this time, I decided to double up on the bottom. Again, it doesn't matter which side you double up and which side you single, as long as 3 sides are single and 1 side's doubled up. Now, on phosphorus, this is a nonmetal, and for nonmetals, we can predict that they would take on a -3 charge, that they would gain 3 electrons. So you notice here I put all 8 dots with that -3 charge. So you notice we had 3 different atoms here. We had the bismuth, we had the antimony, we had the phosphorus that all start off with 5 valence electrons. But you notice as ions, they all looked very different because of what charge they had. So we have to be really careful with that. All right, down here with iodine, first off, as an atom, it has 7 valence electrons. And so then, if I'm predicting my charge, being in group 17, I would predict it to be a -1, meaning it gained that electron. And so I showed all 8 dots with a -1 charge in the brackets. Finally, for xenon, as an atom, it's in group 18, so it has 8 valence electrons. So that just ended up filling everything up. And you notice I didn't ask about a xenon ion because the ion doesn't exist for xenon. It has no purpose in losing or gaining its electrons because it already looks like a noble gas. So now let's talk about this helium atom because this one always gets people and it looks a little different than, say, the other atoms did. First off, helium is in group 18, but remember, it's a lot smaller than the other elements in group 18. So instead of having 8 valence electrons, helium only has 2 electrons to begin with. So first off, I'm only going to show 2 electrons here. Now, something else that's unusual is that for helium, rather than putting 1 on each side and then doubling up, we tend to put those 2 electrons together. And the reason why is, remember that helium only has an S sublevel to it. It doesn't have any P sublevels. And really what these sides are kind of representing is the fact that we have an S and 3 P sublevels that would interact with each other when we're trying to bond. But for helium, first off, it doesn't bond, but not only that, it only has an S sublevel. So no matter what, those 2 electrons are going to end up together. All right, I hope you're feeling a little bit confident with being able to draw a Lewis dot structure for an atom or an ion. Again, eventually what we're going to do is we're going to take all this information and we're going to apply it to compounds. If you have any questions or need any help, please feel free to email me. Bye, guys.